I'm so thrilled to be here and talking about Goroutines and biology. The idea for this talk came out from my just geeking out on biology and some stuff, some cutting edge research that I was getting into over the past couple of years. And so the thing that I learned that blew my mind is that cells pursue goals. And you might be thinking DNA, but it's not DNA. And I'm going to show you the research that I got into, so if you are curious to go deeper. But the researcher that is doing this work, his lab developed a machine to test how these communications are happening. But in any case, I was listening to a lot of YouTube videos and lots of cells communicating and bioorganisms communicating, and all that I could think about was goroutines. Yeah, I know. So I was like, goroutines communicate? Can goroutines communicate with each other? Can I make them do that somehow? So I want to give you a visual of what I'm trying to communicate to you, which is based on this research. When a salamander loses its legs, we know that they regenerate. But so what I learned that blew my mind was there is no DNA directing that regeneration. There is no central control system that tells the body parts of the salamander to regenerate itself. So what happens is, at the level of the cells have a goal. Each cell has a different goal. So they get a signal. It's called a bioelectrical signal that indicates to them that some damage happened and you need to regenerate. And they know what to do. And they talk to the surrounding cells and they each do their thing, and it goes up through the chain of systems. And that's how that body part of the salamander gets regenerated. I don't know, it just blows my mind. Basically, I was thinking, can I pull this off? Can I make goroutines talk to each other, have a goal, and just pursue that goal? And you know what? I did it. So who am I? Like Eric and Johnny said, I'm Carlisia Campos. Been doing golf since 2016. I am a co-founding member of GoBridge. I am the OG of the Go Time podcast, and right? I know that a lot of newcomers here, and that podcast has ended, but it was years in the making, and it's timeless. I highly recommend you check it out. I have worked as an open source maintainer on a couple Kubernetes projects, and currently I'm geeking out on MCP servers. I'm building them, writing about them, is agentic systems and the MCP protocol, and super cool. I'm Carlisia everywhere if you want to follow through or contact me. So what I want to cover, and I hope I do a good job, is I want to share the research that I've been looking at, and I want to show you this library that I built that I called Emerge. And I want to run a simulation so you can visualize what I'm trying to talk, because it's a lot of different concepts. So this is going to be for you to have a new mental model, for you to think, well, what can I create? What else could, if Carlisia created this with Goroutine, what can I create based on some other model? This is also for you if you want to use the library to optimize any task, any workload that is time-based, that requires synchronization. And the beauty is you don't need to add any infrastructure. And this library allows you to measure the coherence gaps in your systems. And this, I can only show you. It's hard for me to explain. And the whole theme of this idea, or of this talk, is it's all goal-based, it's collective problem solving, decentralized. There is no scheduler or Redis, nothing keeps track of what's happening. And this quote is very reflective of the idea. Intelligence as a fixed goal with variable means of achieving it, by William James. Basically, what he's saying is, if an organism has a purpose, a goal, and if the path to that goal gets perturbed or disrupted, and if that organism has a way to get to that goal some other way, that's one way to define intelligence. Of course, we can argue, but it's one way. So, Dr. Michael Levin is a professor at Tufts, and this is the person who I've been following. I get a little bit obsessed for the last couple of years. 2 years, right? 2 years, 2 years. And so I want to stop here because I want to just highlight the papers that are more relevant to this material, to this work that I did, in case you want to check it out. It's really mind-blowing, and the way he talks is excellent. And he comes from computer science as well, and I think that might have something to do with my enjoying the way he explains things, because I don't have a background in biology. I have never taken a biology course, but I really enjoyed reading his papers, some of his papers. So there's those research papers, and if you don't want to read the paper, but you get interested in what this is about, these 2 YouTube videos are so mind-blowing, I can't even. Here, these images are hard for me to explain. It's basically, it's just showing how organisms expand, get coupled, and there are gaps between them, but then they synchronize, and they send signals to each other. And those are the papers where those images came from. So I want to describe a little bit how the emerge agents synchronize. So I'm mentioning agents for the first time. So emerge is a library, and it creates agents that use goroutines to synchronize. And you're going to see in the simulation, it's going to be a lot easier. I have a hard time explaining all of it with words. So basically, I would just want to really emphasize it's decentralized. It's a synchronization algorithm. I also use this Kuramoto algorithm as a base. And that comes from physics, not biology. So basically, I put this whole thing together based on the biology model and this Kuramoto algorithm, so that independent agents, and independent is a very important word here, and in the simulation you will see why. So independent agents can coordinate with each other and achieve a goal. No central control, and I really want to show you codes, but I don't want to show you codes because the simulation shows so much better what this is for and how it works. And also there's so much code that you wouldn't even know where to begin. But I want to show you a little bit of codes because when we get into the simulation, the main question you're going to have is, how do the emerge agents relate to the workloads? How do they get together? So I want to show you just a little bit so you can clear that out and not have that question in your head. Here I'm showing, so I have in this library a few presets. So you can see here, with the builder pattern, is super easy to create a client. The go.distribute loads. This is specific for load balancing. With scale, you give it a scale, it's 20, 200, 2,000, 20,000 maybe? I'm forgetting. And the target coherence that you want. So this preset here is specific, is fine-tuned because there are other knobs. So this is pre-configured and fine-tuned for balancing loads. But you can you can make your own configuration sets with a custom functionality. So this is the part that I really want to show you so you don't have a question. If you see the my service, the first code, the first line inside the struct is where that data is going to be held inside the struct. That's going to be the emerge client. In the pending items, so let's say you have a service already. You just have to add the client inside where you are already calling the client for other things. And then you add a slice there, because that slice is going to hold the items that you want to synchronize. It will be more clear later. Sorry. So then your service is going to process item, and you put basically you're appending the slice, and you're using the Goroutines to make sure things are communicating in a perfect order. And then you add a back. So I'm just trying to show you the codes that drives the mechanism of coordinating the agents. So basically, you're going to use a goroutine to, you're going to start the synchronization, and you can actually there is a way you can start and just do one run, or you can start and do a continuous run. In the simulation, we're going to use the continuous run, so you can see how cool it is. So I have a trigger warning. I'm going to show you the simulation now. But if you get overwhelmed with color-coded things and lots of things on the screen, you might want to leave the room. I'm just saying so you are warned. Let's go. So the first thing I'm going to do a gentle tour of this screen because there's a lot there. I particularly want to show you what is simulation data versus what is emerge data, okay? So in the simulation, there's the simulation package, and it has like the UI package, and it has the separate simulation package, and I did it that way on purpose. So if you look in the simulation package, it's only configuration. So it's just simulating an environment of like sending API requests to batch, for example. So here, this here on the left, this is a simulation. All right, so these workloads, all of this list here is simulated. The tasks column is simulated, the batch column is simulated. Now the in-sync column, this comes from a merge, because you can just like, you're going to be running a loop continuously to run the emerge agents, and then you can get that information. Is this agent in sync? So you get the status. Now, to make it clear, each of these workloads is mapped to one agent. And when I showed you the coupling of the emerge clients with the service struct, and that slice with items, that's how things get mapped. I hope I'm explaining it well. But basically, when a load comes, needs to send requests, the agent will get kicked off, try to synchronize things with the other agents. And for example, this service here is for batching API calls. You can see here on the top. Because we can do batching API calls, we can do load balancing, we can do consensus, latency, any task that requires timing. Now, they need to be independent because each agent that represents that workload, they're going to be working separately, but trying to coordinate. So let me finish giving you a tour, and I will try to explain it better. So here at the top, we have, I'm just showing information here, the goal that is selected, the pattern, because I have presets for different patterns, and the scale. So it can be like a small scale, large scale, etc. And on the right is just information when we select a different setting, which is down here, there is this menu of control. Just for simulation purpose, we can change all of these configs here. And as we pick and choose from the options, this little scenario box will let you know if the combination of pattern and scale that was picked, if it's green, is good. If it's yellow, it's like, nah, not great. And if it's red, it's like, okay, you picked a configuration that is not optimum. It's going to work, or maybe it's not going to work. But what does work mean in this case? So what we are doing here is bashing API calls. Here also are some metrics. Here on the right is this swarm of emerge agents. This shows the gap between each agent in relationship to the target coherence, which is this little blue ball in the center. So going back to what work means. In this case, it's a batch and API calls. So the work here for the agents is to synchronize. So whenever there are multiple agents synchronized, how do they synchronize? They have a timer. Each agent has a timer. It's called a phase. This is part of the algorithm. Whenever the agent is closer to another agent, it speeds up to sync with that agent. So when things are more synchronized, the batching of requests is going to be more efficient. If it's not synchronized, the request will still be sent, will still be batched, but it won't be efficient. So what does efficient mean in this context? It means that if the more tasks that the batch has, the more efficient it is. So a batch with one task is really not efficient at all. So now I'm going to press a key, and the simulation is going to start running. So I'm going to go step by step instead of like let it run and we have no idea. You can't. I know what's happening, but you're not going to be able to orient yourself. I'm going to do like one step and then show you what happens next. So here I have the simulation configuration is start up in a not so great coherence. So you see the swarm here on the bottom right. They like spread out. For batching things, this is not great because they like not synced together. What we want here is to bring that these agents start organizing amongst themselves and get closer to the blue dots. And up here we set the target coherence. Obviously, this is going to be different depending on your needs. So, right? What is the hardware you have? What's the infrastructure? What is the cost savings you want to achieve? But we started out with the coherence, like at 20% is way below 90. So when I press the next step, they synchronize really quickly. So with the simulation, I have random numbers, like random like waits for like this random amount of time. This is all time-based. So now the agents are close together. So when the agents are close together, if you look here on the left, the task column and the batch column, and on the bottom here, I have the total number of tasks and total numbers of batch tasks. So basically, the tasks are being sent, and when it's red, like this one, the tasks that are going to be sent are not going to be that many. But when it's green, it's going to be more requests sent to the batch. Because what's happening here, and I'm not explaining really well, is that if agents are, let's say there are only 2 agents. If they're very far apart, they're not synchronized, so the request is just going to be sent because there is no synchronization with the agents. But if these 2 agents are close together, they're going to like one is going to wait for the other, and the tasks are going to batch, and then they're going to accumulate, and then because they know there is another agent that's close by, one agent is going to wait, and then the task accumulate, send, and then the other agent is going to wait for the next set of tasks, and then send, and on and on and on. But if they're far apart, it's like there is no handoff here because it's too far apart. And the far apart or close together is based on timing. which is based on that algorithm. Let's see. Okay. So this is for batching API calls. Now I want to show the distributed load because it's completely opposite. Okay. So now, if you look at the swarm, the red is bad, right? It should be obvious. They're close to the center, and then you might be asking yourself, well, but being close to the center, isn't that good? But you're only thinking that because I showed you the API batching first. So this is very contextual. So for the API batching, we want things to synchronize close together. But for distributed load, we don't want that. We want the opposite. We want to distribute. Like the more evenly distributed things are, the better. So that's why the coherence started at a higher percentage, and the target coherence for this is much lower. So I'm pressing the key here to step through. And you see that things are starting to get better. A little bit of green, more green. Okay, it goes back and forth because it's random. But the idea is that, let's see. Let me just, okay, see when they spread out more, it's okay. The balance here for this workload is it was well balanced or is better balanced. This simulation, I still need to do a lot of work. These are the only two type of goals that are really working well. But if you see on the bottom, there is consensus, a goal to decrease latency, and I have to work on those. But if you want to play with it, I think I oriented you a little bit. Now, the next action item here for you is explore the emerge package, if you like. There are tons of docs. There are so many different concepts for this library, and I created a document for each one of them. So you can install emerge, and it's really not a lot of codes, but there is a quick start guide there that will help you. You can also monitor what is the gap, how far apart are those requests being sent. Maybe they close together, but they shouldn't be, or vice versa. And that's it, but one more thing. This really is 3 libraries. Emerge is the first one that I'm working on, and is a time-based, synchronization-oriented system. And there's going to be a navigate. So emerge is for when you want things to be done. Sometimes you want them to be done quickly, sometimes you want them to be done farther apart. The navigate library is going to be where. For example, let's say you have requests, and you're sending those requests to find something. Let's say there's a bunch of configurations in a system, and you want to find a specific set, maybe the best or the worst. So that's what navigate is going to be able to do. And glue is going to handle the what. For example, let's say you have some system is failing, and there's parameter A and B, from A to Z. And what glue can do is find what combination of parameters are causing some system failure, for example. So it's when, where, and what. And this is all decentralized operations, all based on this idea of biological systems being able to pursue a goal. Now, I haven't worked out the algorithms for the last two. I don't know what algorithm I'm going to have to use as a base. And, if you are excited about this, you can go to the repo and try and let me know. Let me know your experience. And maybe, let's build this together. That's the link for the library, for the project. And that's my website. I write stuff. And thank you for taking the time to be here.